All right, let's look at the worked out solutions for our sample test for Chapter 4. Question number 1, they ask us to find the differential for the equation. So remember that a differential is going to be dy is equal to the derivative times dx. So all I need to do is find the derivative, and then I can say dy is equal to that derivative we just found times dx. That's my differential. Then for number 2, it said, okay, to evaluate that differential when x equals 2 and dx equals 0.1. So we're just going to come back. This is that same equation we created in number 1. We're just going to come back and put 2 in for x, put 2 in for x, and put 0.1 in for dx. And then we can simplify to get 3.6. Number 3, they ask us to find the linear approximation for y is equal to the 4th root of x at x is equal to 16. So I'm going to rewrite that as x to the 1/4 so that it's easier to take the derivative. So if I have x to the 1/4, then the derivative of that would be 1/4 x to the negative 3/4, and that would be the same thing as 1/4, and then you can see our x to the 3/4 down here in the denominator since it was negative. All right, so I know that my a value is 16. So when x is equal to 16, to find y, I'm just going to plug 16 into the equation. So that would be the 4th root of 16. So y is the 4th root of 16, or 2. So there's my ordered pair 16, 2. That's going to be a, f of a. So we can come over then, and again, in the place of f of a, we're going to put 2. In the place of a, we're going to put 16. So that would be x minus 16. So you can see that here. That's where our 2 comes from, and our x minus 16 comes from. Now all we need is the derivative at a. So let's take our derivative, and let's plug 16 in. So if we take 16 and we plug it in, we're going to put 16 right there in the place of x. I'm going to do the 4th root of 16 first before I cube it. So the 4th root of 16 is 2. And then I can cube the 2 and get 8. So 4 times 8 would be 32. So the derivative at a would be 1 over 32. That can go right here. And that is our equation. All right, so then for number 4, they ask us to use that to approximate the value of the square root, the 4th root of 15.99. So what I'm going to do is in the place of that x right there, I'm going to put 15.99. And so you can see that that's exactly what we did. In the place of x, we put 15.99. So if you go back again, 2 plus 1 over 32, x minus 16, 2 plus 1 over 32, x minus 16. All we've done is just put 15.99 in the place of x. So 15.99 minus 16 is going to be a negative 0.01, or negative 1/100. So 1 over 32 times 1 over 100 would be 1 over 3,200. So 2 minus that would be 1, and 3,199 over 3,200. Now if you put that in to get a decimal approximation, you get 1.9996875, and the actual value of the 4th root of 15.99, you can see is this is a really good approximation of what that actual value would be. All right, then for number 5, they gave us a graph, and they asked us to identify the local extrema and the absolute extrema. All right, so I have a local maximum where my graph changes from increasing to decreasing. So that would be right here at negative 2, 2, and right here at positive 2, 2. Then I have a local minimum where my graph changes from decreasing to increasing. So you can see it change from decreasing to increasing right here at 0, negative 1. Your endpoints cannot be relative extrema. They can't be local or relative maximums and minimums because the graph is not changing from increasing to decreasing or decreasing to increasing there. The endpoints can, however, be absolute maximums and minimums. So if we're looking for the absolute maximum, that's going to occur at negative 2, 2, and 2, 2. So the absolute maximum is 2. It just happens at 2 different places. And then the absolute minimum is right here at negative 4, negative 2. All right, then for number 6, they ask us to identify the critical numbers. Remember that critical numbers are where your derivative equals 0 or where your derivative doesn't exist. So first off, let's find the derivative. So we're going to do denominator times derivative of numerator minus numerator times derivative of denominator all over denominator squared. Then I'm going to distribute here, so 6x times x would be 6x squared, and 6x times negative 5 is negative 30x, and then the minus 3x squared. So 6x squared minus 3x squared would be 3x squared minus 30x over x minus 5 squared. Now, where my derivative equals 0 is where my fraction is equal to 0. Well, the only way a fraction equals 0 is if its numerator equals 0. So we're going to set the numerator equal to 0 to find out where our derivative equals 0. Take out your greatest common factor of 3x, and that'll leave you with x minus 10. Set each of those factors equal to 0, and we'll get x equals 0 and x equals 10. Then, where the derivative doesn't exist is where I would get 0 in the denominator, and so I'm going to set my denominator equal to 0 to find out where that is, and that is at x equals 5. So 0, 5, and 10 would be my critical numbers. All right, then for number 7, they ask us to check the hypotheses of Rolle's theorem, and if it checked out, to then apply Rolle's theorem. So we have this polynomial equation from negative 2 to 2. So step number 1, it has to be continuous on the closed interval, being equal to those endpoints. Well, we know polynomials are continuous everywhere, so that's fine. And then it has to be differentiable on the open interval, so parentheses here, it doesn't have to include the endpoints. So I know that polynomials are differentiable everywhere. I also could actually take the derivative and look at the derivative and look at its domain and see that it is going to exist everywhere. So that derivative exists everywhere, so it's differentiable everywhere. So then the last thing is that f of a has to equal f of b. So we're going to take a, negative 2, and plug it into the function. So if I plug negative 2 into this function, I get 0. And then I'm going to take positive 2 and plug it into the function. So when I plug in positive 2, I also get 0. So since f of a equaled f of b because they both equaled 0, that is the third hypothesis. All 3 hypotheses work to be true. So I can apply Rolle's theorem, which says there will be a value within this interval where the derivative equals 0. So I'm going to take my derivative. So the derivative of x cubed minus 4x would be 3x squared minus 4. Set that derivative equal to 0. I'm going to add 4 to both sides, divide by 3, and then take the square root. Don't forget to put in your plus or minus. So the square root of 4 is 2, and then we'd have the square root of 3 in the denominator. So let's get that radical out of the denominator. We're going to multiply top and bottom by the square root of 3. So that would give me plus or minus 2 square roots of 3 over 3. 2 square roots of 3 over 3 is approximately 1.1547. So you can see both the positive and the negative would be within that interval. So both of them are going to be solutions. All right, then for number 8, they asked me to verify the hypotheses of the mean value theorem, and if they were true, then to apply the mean value theorem. So here's my equation. So I've got x to the 4/5, or the 5th root of x to the 4th, from negative 1 to 1. So first I need to check to see, is it continuous? All right, well, this is a radical. And so with a radical, it's going to be continuous within its domain. You can take the 5th root of anything. You can take the 5th root of a positive number, a negative number, or 0. So radical functions are continuous on their domain, and the domain for this is all real numbers, so it's perfectly fine from negative 1 to 1. Then I want to check differentiability, and the easiest way to do that is just to take the derivative. So if I had x to the 4/5, the derivative of that would be 4/5 x to the negative 1/5. So we could write that as 4/5 and then x to the 1/5 in the denominator. So there's my derivative. that derivative will not exist anywhere the denominator equals 0. So let's take our denominator and set it equal to 0. So I'm going to divide both sides by 5, and I'll get the 5th root of x equals 0. Raise both of those to the 5th power, and I'll get x is equal to 0. So this derivative doesn't exist at x is equal to 0, but that is in the interval between -1 and 1. So that second hypothesis fails. It's not differentiable on the open interval, and so therefore I cannot apply the mean value theorem. All right, then number 9, we had Newton's method, and for Newton's method, remember that you're going to give your setup equation, x minus the original divided by the derivative, and then you're just going to give the list of successive approximations. That's the only work that you have to show. So here's our original function, and we've got its derivative in the denominator, and they also told us where to start. So let's go look at our graphing calculator. So I am going to start with -1.2, so I'm going to store that value to x. And then I went ahead and previously typed my equation just to make it a little bit faster. But when you type it in, you're going to do x minus the original divided by the derivative. And so when I hit enter, it's going to plug 1.2 in for each of those x values. And so the -1.3379744684 is my second approximation. Let's store that to x. And then go back up and grab our equation again. And this time it will plug in that second approximation and give me my third approximation. So the -1.328320034 is my third approximation. I've stored that to x. Now I'm going to go back and grab my equation. And it's going to plug in that third approximation, and there's my fourth one. And we're going to keep following that same process, writing those answers down that we get, until we get the same answer twice in a row. And when I get the same answer twice in a row, I can stop. Now, if you'll notice, this is really close. The last two numbers there, 56 and 57, so we're getting really close to our answer. Probably just one more time and we'll have it. And so again, go back up and grab your equation. This time it'll plug in that last approximation, and yes, I do get the same answer twice, and so I know that I can stop, that is my final solution. So again, you're just going to list each of those successive approximations that you got. All right, then we switch to the non-calculator or the non-graphing calculator page. You can use the scientific if you'd like. But on the non-graphing calculator page, they ask us to find the absolute maximum and minimum for this function on the interval from -1 to 4. Your absolute maximum or minimum can occur at your critical numbers or at your endpoints. So let's find the critical numbers first. Remember, you find critical numbers by taking the derivative and setting it equal to 0, or seeing where the derivative doesn't exist. So our derivative of x squared plus 3 is 2x. If we set that equal to 0, divide both sides by 2, we'll get x equals 0. And there's nowhere that 2x doesn't exist, so that is my only critical number. So I need to take my critical number of 0 and my two endpoints of -1 and 4, and I need to plug them back into the original equation. I'm looking for the absolute maximum and minimum of the original equation. So you can see the highest y value that I got was 19. That's my absolute maximum. The lowest I got was +3. That's my absolute minimum. All right, then for number 2, we're going to take this cubic function and we're going to label where it's increasing, decreasing, where it has maximums and minimums, where it's concave up and down, where it has points of inflection. So we're going to need the first derivative and the second derivative for that. So to begin with, here's my first derivative, 3x squared minus 12x. Let's set that equal to 0 and solve. So I could take out my greatest common factor of 3x, and that would leave me with x minus 4. Set each of those equal to 0, and I'll get critical numbers of 0 and 4, and there's nowhere that derivative doesn't exist. So let's come make a graph of the first derivatives. There's my critical numbers of 0 and 4. I need to find out where this derivative is positive and negative, so I'm going to pick a test point. I'm going to use a +1. So I'm going to take positive 1 and plug it into the derivative because I'm trying to figure out where the derivative is positive and negative. If I plug in positive 1, I'm going to get negative 9. So that means that it's negative right here. Cross a single critical number, the sign changes. Cross a single critical number, the sign changes. So there is my first derivative sign graph. Now we can use that derivative sign graph to figure out that anywhere my derivative is positive, then my original function is increasing. Anywhere my derivative is negative, my original function is decreasing. So I can see that it was positive from negative infinity to 0, so increasing there. And then it was negative from 0 to 4, so decreasing there. And then it was positive from 4 to infinity, so increasing there. Anywhere my original function changed from increasing to decreasing, or my derivative changed from positive to negative, I'll have a relative maximum. So relative max at 0. Anywhere my original function changed from decreasing to increasing, or my derivative changed from negative to positive, I'll have a relative minimum. So I'll have a relative minimum at 4. Now, for both 0 and 4, they are the maximum and the minimum of the original function. I plug those back into the original equation, not back into the derivative. So I'm going to plug in 0 to the original function and get 0. I'm going to plug in 4 to the original function and get negative 32. And here's a reminder about that right here. Okay, so for concavity and points of inflection, we need the second derivative. So if we take the derivative of 3x squared minus 12x, that would give us 6x minus 12. We're going to set that equal to 0, so take out the greatest common factor of 6, and that leaves us with x minus 2. So that gives us x equals 2. So let's come make a sign graph for the second derivative now with our only root at 2. All right, because again, there's nowhere that derivative doesn't exist. All right, so I need to figure out where the second derivative is positive and negative. So I'm going to pick a test point of 0. And again, I'm trying to make a sign graph for the second derivative. So I plug the 0 into the second derivative to see where it's positive and negative. So I get a negative 12. So that means it's negative here. Cross a single root, the sign changes, positive here. So my graph is going to be concave upward anywhere the second derivative is positive. That's from 2 to infinity. And it's going to be concave downward anywhere the second derivative is negative. So that's from negative infinity to 2. Anywhere my graph changes concavity. It changes from concave up to concave down, or concave down to concave up. Anywhere the second derivative changes sign from positive to negative or negative to positive, I am going to have a point of inflection. So that is at 2. Again, I'm going to take 2 and plug it back into the original equation, because when I'm trying to find relative maximum, minimum, or point of inflection, those are of the original function, so I plug back into the original function. All right, then for number 3, trying to find our horizontal and vertical asymptotes, we need to make sure that we don't have any common factors. So x squared plus 3 doesn't factor. X squared minus 1 would be x plus 1x minus 1. So no, there's nothing in common that could cancel out. So first, to find my horizontal asymptote, the way we did that in pre-cal was we compared the degree of the numerator and denominator. If the degree of the numerator was larger than the denominator, then we didn't have one. If the degree of the numerator was smaller than the degree of the denominator, it was automatically y equals 0. And if the degree of the numerator equaled the degree of the denominator, it was y equals the leading coefficient of the numerator over the leading coefficient of the denominator. So if you look at ours, the degree of the numerator is 2 and the degree of the denominator is 2. So since they're equal to each other, it's going to be y equals leading coefficient over leading coefficient. The leading coefficient here is 1 and here is 1. So that would be y equals 1 over 1, or y equals 1 for our horizontal asymptote. The calculus way that we learned to do that was you take the limit as x approaches infinity or negative infinity of the function, and if you get a numerical answer, that value will be a horizontal asymptote. So one of the tricks that they showed us for evaluating a rational function was to divide everything by the highest power of x in the denominator. The highest power of x in the denominator is x squared. So I'm going to divide every single one of these pieces by x squared. So you can see that's what we've done here. So x squared divided by x squared is 1. 3 over x squared is 3 over x squared divided by x squared is 1, and then 1 over x squared. Now, we haven't taken the limit yet. All we've done is just some algebraic simplification. But if you take the limit of a constant, you get that constant. If you take the limit of a number divided by a variable when you're approaching infinity, we have a rule for that it is 0. Because your numerator is staying the same, your denominator is getting bigger and bigger, your overall fraction gets smaller and smaller and goes to 0. Limit of a constant is that constant. Limit of a number divided by a variable when you're approaching infinity is 0. So that would give us 1 over 1 or y is equal to 1. So same answer either way. All right, vertical asymptote, we learned in pre-cal that if you had no common factors, you could set your denominator equal to 0. So if we set our denominator equal to 0, we'll get x is equal to a positive and a negative 1. Those are my vertical asymptotes. The calculus definition for that is that if you take the limit as x approaches a number and you get infinity or negative infinity as an answer, then that number was a vertical asymptote. So sure enough, if I take the limit as x approaches 1 from the right, you can imagine if I'm plugging in 1 from the right, I'm putting in like 1.1, 1.01, 1.001. So up here in the numerator, I'd have 1 plus 3, I'd have 4. My numerator is staying the same, my denominator is getting smaller and smaller, so what's my overall fraction doing? It's getting larger and larger, it's going to infinity. So since when I take the limit as x approaches 1 from the right, I get infinity, then x equals 1 is a vertical asymptote. All right, we could do the same thing with the limit as x approaches a negative 1 from the left. If I'm approaching negative 1 from the left, I'm using values like negative 1.01, negative 1.001, negative 1.0001. So when I plug in up here, I'm going to get 1 plus 3 is 4. My numerator is staying the same. My denominator is getting smaller and smaller and smaller. So my overall fraction gets larger and larger and larger and goes to infinity. So since I was able to take the limit approaching negative 1 and get an answer of infinity, that means x equals negative 1 is a vertical asymptote. So again, whether you use the method of pre-algebra or the method of calculus, you get the same thing. All right, then for number 4, we were evaluating some limits, okay? So again, here is another one where we have the limit as x approaches infinity of a fraction. And so that method we had a moment ago of dividing everything by the highest power of x in the denominator, highest power of x is x squared. So we're going to divide every one of these by x squared. So x cubed divided by x squared, 4 divided by x squared, and x squared divided by x squared. So that would leave me with just x in the numerator, 4 over x squared, and then x squared over x squared would just give me 1. All right, so if I plug in infinity, I'm going to get infinity in the numerator. Again, we're not saying infinity is a number. We're saying that infinity is the symbol that represents something getting larger and larger and larger without bound. It's just easier for us to write infinity than to write something getting larger and larger and larger without bound every time. All right, then the limit as we approach infinity of a number over variable is 0, and the limit of a constant is that constant. So we'll get infinity divided by negative 1, which would be negative infinity. All right, then for the next one, if I plug in infinity, I get infinity minus infinity. That is not something that we can figure out. So remember, we would try to use anything we could algebraically to change that to a different format. And so if you'll notice, I have a greatest common factor of x here I could take out. So now that I've written it in a different format, now look what happens when I plug in. I'm going to get infinity and then 8 minus infinity. All right, well, if you take 8 and you subtract infinity, you're still going to have negative infinity. So infinity times negative infinity would be negative infinity. All right, then for the next one, we've got the limit as x approaches 0 of 1 minus cosine over x. So if I plug in 0, I'm going to get 1 minus the cosine of 0 over 0. The cosine at 0 is 1, so 1 minus 1 over 0 would give me 0 over 0. That is one of the forms that we can use L'Hopital's if we get 0 over 0 or an infinity over an infinity. So I'm going to come down here. Remember, we have to put the capital H on here to show these two are equal. That's the only way they can be equal. So according to L'Hopital's, I take the derivative of the numerator, so the derivative of 1 is 0, derivative of cosine is negative sine, so negative sine would be positive sine, derivative of x is 1. So now if I plug in, I'm going to get sine 0 over 1, and the sine at 0 is 0, so I'd get 0 over 1 or 0. All right, then look at the next one. Limit as x approaches infinity of e to the x over x cubed. If I plug infinity, I'm going to get e to the infinity over infinity cubed, or infinity over infinity. So I can use L'Hopital's. And so remember to write your capital H every time you use L'Hopital's. So the derivative of e to the x is e to the x, and the derivative of x cubed is 3x squared. If I plug in infinity, I get e to the infinity, which is infinity, and 3 times infinity squared, which is also infinity. So I'm going to use L'Hopital's again. So the derivative of e to the x is e to the x, and the derivative of 3x squared is 6x. So now when I plug in, e to the infinity is infinity, and 6 times infinity is infinity. So I can use L'Hopital's again. And you'll notice that we're making progress, though. We had x to the third, x to the second, x to the first. So now when we take the derivative of e to the x, of course, it's still e to the x, but the derivative of 6x is 6. So now when I plug infinity, I get infinity divided by 6, which is infinity.